So tonight we will be discussing chapter 9, which is, can you see the presentation here?
Yeah, it's all clear.
Good, okay. It would be over the center of mass and linear momentum. See our objectives here. So, if you look at an object that is sort of oblong, kind of oddly shaped, in this particular example, you can see here a baseball bat. The motion of that object, as it says here, can be fairly complicated. For the ease of modeling's sake, if we reduce things down to a point that may or may not be on the object, but if we can reduce it down to a particular point and we can follow that particular point, we can model the motion of the entire object. And that point is going to be called the center of mass. The center of mass is going to act just like a round object, a sphere, a ball that we've been throwing near the surface of the earth, that kind of thing. And it's going to be tracing out parabola as it's thrown. And just as in the case of a thrown ball, the x direction does not depend on gravity, but the y direction motion will. And as it says here, all other points rotate around that specific point in some fashion. So this point is going to be called the center of mass. And the center of mass of a system of particles is going to be the point that moves as though all of the system's mass were concentrated there. And all external forces are going to be applied there. For two particles that are going to be separated by a distance d, where the origin is chosen at the position of particle 1, let's see if I can draw a small picture here. So we've got that, and we've got mass at one end, and we've got the mass at the other end. And we draw our axis such that x is equal to 0 at that particular point. We'll call this one mass 1. This one over here will be mass 2. So if we do that, and we call the distance that separates them d, you can see that the center of mass is going to be determined by this particular formula. However, if you have two particles, and let's say you don't necessarily want your origin to appear at the position of one of those particles for whatever reason, then the center of mass is determined in sort of a weighted average sense, where you've got the mass of 1 times the position of 1 plus the mass of 2 times the position of 2 divided by the sum of the mass. Now, the center of mass is going to be in the same location regardless of how you define the coordinates. I mean, it doesn't really matter where you put the origin. That center of mass in relation to the two objects is going to be at the same point. So as you can see here in the diagram, that the center of mass is here, the two particle system. Whether or not you shift the axis a little bit this way or this way or this way, it doesn't really matter. The center of mass is going to be in between those two. Obviously, if we want to extend this concept out for n particles that all have different masses, then the center of mass is going to be the sum of the product of the mass and the position for each one of these n objects, divided by the total mass. And if you want to write it in shorthand using sigma, this is how you would go about doing it. In 3 different dimensions, you can find the center of mass along the x-axis, y-axis, and z-axis. It's the same formula, you're just changing out the variables. If you want to write it in terms of vectors, where you can combine x, y, and z and whatever other dimension you might like, then the center of mass of our vectors here is going to be computed by this particular formula. So for solid bodies, we are going to take the limit of this infinite sum of infinitely small particles, and we can conduct this with integration as we move through. Obviously, we can take the 1 over m out because it's independent of the variable in any dimension. So one way we can make sure that we simplify the process here is to not consider objects that lack a uniform density. If you really want to make things more complicated, all you have to do is to make density a function of position, and you've got yourself a nightmare of a problem. So if you assume that it's just simply uniform density, it doesn't matter where you go in the object, it's always going to be the same density, it simplifies matters. The density is going to be considered the derivative of mass with respect to volume. Obviously, if you add all of those up, then you've got m over v. If you want to go through and substitute this result into the equations that you have here, this is going to end up being your result. So you can bypass one or more of those integrals if the object has symmetry, which can help you out greatly. So the center of mass lies at a point of symmetry. Obviously, if you have two masses that are equal and they're separated by a distance, and the center of mass should lie directly in between them. It will also lie on the line or plane of symmetry, and it doesn't have to be on the object. And the notes here bring up, consider a donut. A donut is going to be, obviously spread out all the way around, but its center of mass is going to be in the middle of it. So it doesn't necessarily have to rest on the object. So let's take a look at this particular graph here. We've got a square that has its center there in the middle of the axes, and we have 4 corners. It is a uniform square plate, so there's not one side that's more dense than the other, and all of the corners are identical. So if you were to look at that just as is, where would you consider the center of mass of that plate to be?
Just at the origin of the axis?
Yeah, it's right at the origin. What if you go through and you remove square 1? where does that center of mass shift into?
Would it shift into the third box or?
Yeah, or the what's considered to be quadrant 4. If you do it using the trigonometric definition, where this is quadrant 1, this is quadrant 2, this is quadrant 3, and then this is quadrant 4. But yeah, if you look there for the little box that's labeled as 3, it would shift into this particular box, and it will also shift along the line y is equal to negative x. So that line of symmetry that goes through there, it's going to shift along that line. What happens if I go through and I remove this square and this square? Where would it go?
It'd be on the y-axis, right? But it'd be all in the negative y-axis.
Yeah, probably somewhere around in this area, but along the y-axis and in the negative region. What happens if you remove this square and then this square?
Remove square 1 and 3, you said?
Would
it still be in the origin?
That's right. And then what happens if you remove this, and this square?
It'd be the center of the remaining square, right? In quadrant, would that be 3?
Yeah, it'll be in quadrant 3, somewhere along the line of y is equal to x. And then what happens if you remove all 4 of these squares?
Origin, right?
Yep. So you're getting the idea of the symmetry here, and how removing it on one side will cause it to shift to the other. So that's good. So here's another example. Let me go ahead and kind of blow this up a little bit. Move this over here. Still need to go up a little bit. So our task is to find the center of mass of a disk with another disk taken out of it. So we've got our original disk, and then somebody comes along with a cookie cutter and takes that out. So the way you go about doing this is we're going to find the center of mass of each individual disk. And it's asking you to start at the bottom and then work up. So if you take a look here before it's cut, for this particular disk, you would expect the center of mass to be right here in the middle. So then somebody comes along and says, hey, I want to cut this section out of it. So if you look at that, the center of mass is right here in the little disk. If you take the position of the center of mass of each one of these and sort of project it here, you begin to see that if you were to remove this particular disk, that the center of mass is going to shift because this mass is no longer present. It shifts over this way to the right. All right. So we'll move on to Newton's second law. All right. So the center of mass motion is going to continue unaffected by forces internal to a system. So collision between billiard balls is what it's mentioning here as an example. So motion of a system center of mass is going to be the result of the net force, and the net force is going to be the total mass times the acceleration of the center of mass. So again, that capital M there is there to remind you to sum up the masses of each individual part. And equation 915 there is showing you how, if you take this particular vector and you break it out in each dimension, this is what it would look like. And the reminders here are F net is the sum of all external forces, M total. M is the total constant mass of the closed system, and the acceleration of the center of mass is the center of mass acceleration. So the reminder of Newton's second law here is force is equal to mass times acceleration. So using the center of mass motion equation, if you're looking at billiard collisions, again, those are considered to be internal forces. It is part of the system, not external to it. Therefore, the net force sum of external forces is 0, and so the acceleration of that center of mass doesn't change. If you're looking at a baseball bat, acceleration is going to be equal to gravity, so the center of mass is going to follow a gravitational trajectory. If we look at an exploding rocket, the explosion forces are internal, so only the gravitational force acts on the system, and the center of mass is going to follow a gravitational trajectory. And the only thing that might change that would be air resistance that is working against the system. Okay, so two skaters are on a frictionless ice, and they hold opposite ends of a pole of negligible mass. An axis is obviously going to run through it with the origin at the center of the mass of the two-skater system. One skater, Fred, weighs twice as much as the other skater, Ethel. So where do the skaters meet if Fred pulls hand over hand along the pole so as to draw himself to Ethel? And I will give you a hint. In all three of these cases, they're going to end up at the center of mass. So it's true if Fred pulls hand over hand along the pole to draw himself to Ethel, or if Ethel pulls hand over hand to draw herself to Fred, or if they both do it. So the system consists of all three of those objects, Fred, Ethel, as well as the pole. Forces are considered to be internal. Therefore, the center of mass will remain in the same place. Since the origin is the center of mass, they will meet at the origin in all three cases. Now, here's a very important definition. Linear momentum. Linear momentum is going to be defined as the mass times the vector, the velocity vector. The momentum is going to point in the same direction as the velocity, and it can only be changed by a net external force. Here's a key point at the bottom of this. The time rate of change of the momentum of a particle is equal to the net force acting on the particle and is in the direction of that force. And a lot of times you're going to see Newton's second law written like this, where the net force is going to be equal to the change in momentum over time. So if you look at the figure on the right, that figure gives the magnitude of the linear momentum versus time for a particle moving along the axis. So a force directed along the axis acts on the particle. Rank the 4 regions indicated according to the magnitude of the force with the greatest first. So if you look at this, you've got momentum plotted against time. And how did we just define force? I'll give you a hint. Force is defined as the change in momentum with respect to time. So which one of these, and if we're looking at it in that context, we can look at this particular graph and we can say we can focus in on the slope, because the force is going to be proportional to the slope of these lines. Which one of these lines has a slope that's not 0?
1 and 3.
That's right. 2 and 4 don't have any slope to them. I mean, their slope is 0. So if we're going to rank the 4 regions indicated according to magnitude, and for magnitude means that we're going to take the absolute value of whatever the slope happens to be, what we're going to rank the 4 regions indicated according to the magnitude of the force, with the greatest being first. Which one of these lines is going to have a magnitude of slope that is greater than any of the rest of them?
1, right?
That's right. 1 happens to point up, and its incline is going to be sharper than anything else. What would be the next greatest magnitude of force after 1?
3.
Right. Even though it's pointed down, at the very least, it's pointing in a direction that's not horizontal. So our competition here is going to be between a line that points down but doesn't point down as quickly as line segment 1, whereas 2 and 4 just kind of meander along in a straight line. So the next value is going to be 3. Then after 3, which one of these has the greater force?
2 and 4, right? The slope is 0.
Yeah, their slope is 0. Doesn't really matter if 4 is longer than 2. The slope of both of those is going to be 0. So now here's another question. In which region is the particle slowing down?
It'd be 3, right?
And why would that be?
Because the slope is negative.
That's right. The slope is negative, which means that the momentum with respect to time is declining, which means that the velocity must be decreasing. So we can sum the momentum for a system of particles, just like we had before. So the total momentum is going to be equal to the total mass times the velocity of the center of mass. So if you're looking for the net force on a system of particles, as we had said before, it's going to be dP dt. In this particular case, we replace the small p with a big P and carry forward in the same fashion. So the key point here is that without a net external force, in other words, something external to the system acting, total linear momentum of a system of particles cannot change. Okay, collision and impulse. So in a collision, momentum of a particle can change. We're going to define the impulse acting during a collision, and that's going to be represented with J. And that is going to be equal to the integration of the vector force, which is depends on time, dt. So what this means is that the applied impulse is going to be equal to the change in the momentum of the object during the collision. So the linear momentum impulse theorem is what's stated here in equation 9.31. So given the average force and duration, we're finding here that the impulse is going to be equal to the product of the average force times the change in time. And since we are integrating the force with respect to time, all we are really getting is the area under the curve. All of that area, as it's shown here, could be changed such that you're having a maximum force impact at a particular time, or it could be just a uniform force that's spread out over quite a bit of time. It really kind of depends on the situation, because in both cases, if you look at the average here, the average force is just kind of spread out from the initial time up to the final time. That area here is going to be the equivalent to this area up here. Does that kind of make sense?
As you explained it, yeah.
Okay. That's good. Because this question right here is going to try to reinforce that. So you've got a paratrooper whose chute fails to open and he lands in the snow. That could be she. Well, no, it says here. He is hurt slightly. Had he landed on bare ground, the stopping time would have been 10 times shorter and the collision lethal. Does the presence of the snow increase, decrease, or leave unchanged the values of A, the paratrooper's change in momentum? So let's stop there and let's kind of think about that. If the snow were there, or if it were not there, what would the change of the paratrooper's momentum be? It would go from whatever momentum he has falling from the sky to what? Well, if you were thinking about saying 0, then you'd be right. Because obviously the momentum, which is going to be mass times the velocity, when the paratrooper lands, how fast is he going to be going eventually as he comes to a stop? Because speed is eventually going to become 0. So we've got the paratrooper landing, he comes down, hits the ground, whether or not there's snow, his momentum is going to be stopped. And it doesn't matter, again, it doesn't matter if there's snow on the ground or not. So that answer is going to be that his change in momentum is going to be unchanged. So here, it gets even wilder. Does the presence of the snow increase, decrease, or leave unchanged the impulse stopping the paratrooper? The impulse is the same as what? It's going to be the same as a change in momentum. And here we decided that the change in momentum, whether there's snow or not, there's no difference. The same change in momentum is going to be the same regardless. So what about the impulse? Is the impulse going to be the same?
It should be the same, right?
Right, exactly. So it'll be the same. So that doesn't change. Here's the question that is going to take even more thinking to kind of get your head around. I know, because as I was reading this question, I was trying to conceptualize what was going on, and it took me a little bit. So does the presence of the snow increase, decrease, or leave unchanged the value of the force stopping the paratrooper? This and this is going to be an example of whether or not you have snow on the ground or not. As is stated in the problem, had he landed on bare ground, the stopping time would have been 10 times shorter and the collision lethal. We've already established that the impulse doesn't change, right? If there's snow on the ground, as compared to there not being snow, what happens to delta T?
It
If there's,
increases, right?
say again?
If there's snow on the ground, the time increases, right?
Right. If there's snow on the ground, that delta T is going to expand by 10 times. In order for this to remain the same value, what happens to this guy if this increases tenfold?
It decreases proportionally.
Exactly. It goes down. It's 1/10 of what it used to be. And because of that, the force stopping the paratrooper is considered to be decreased. That's why he didn't die. That will take probably a little bit of thinking, but do you at least see the general direction that that's pointing?
Yeah, I understand most of it now.
Okay. All right. Like I said, that's a thinker, but that's what it's trying to get across. So now for a steady stream of N projectiles, each undergoes a momentum change of delta P. Obviously, if you have N projectiles coming in aimed at a target, change in momentum is going to be delta P for each one of those. That's where the N comes from. And therefore, the impulse to this is going to be minus N times change in the momentum. The average force, obviously, we're just going to take that formula that we looked at a couple of slides ago, take the delta T, put it down here, divide J by that delta T. The average force in this particular case, we're going to take this definition of J, rewrite it here. And then as we do that, then we notice that the average force is going to be the same as minus N over delta T times M times the change in V. All this is replacing this with m delta V. If the particles stop upon impact, then the change in velocity is going to be minus V. If the particles bounce back with equal speed, then the change in V is going to be minus 2V. So the product N times M is the total mass for N collisions. So then they turn around and write that the average force is going to be equal to minus the change in M over the change in V, over the change in T times the change in V. All right, so here's another example. The figure here is an overhead view, so we're standing up looking down on a court, of a ball bouncing from a vertical wall without any change in speed. So it hits here and then goes off this way. So the speed, meaning not the velocity, which is a function of both position and magnitude. This is just the speed. So the magnitude of this thing hasn't changed. So let's consider the change in momentum in the, with the ball. If we look just in this direction, would there have been any force applied such that the change in momentum would be positive, negative, or zero? Is there any force that's changing that?
There isn't any force.
Right, there isn't any force. It's just bouncing off the wall. So there's no change in the momentum in the x direction. What about the change in the momentum in the y direction? Is that change positive? Is it negative?
Would it be positive?
It would be positive if we go back. Change in V is going to be velocity final minus the velocity initial. If we look at here, the final velocity is going to be in the positive y direction, whatever that amount happens to be. Over here, that velocity was headed in the negative direction. So the final velocity is going to be positive. We're going to subtract the initial velocity, which happens to be negative. So we've got positive minus a minus. So positive plus a positive. And so you would be right. The change in the momentum in the y direction should be positive. So what's the direction if we were to write that as a vector? Would it point along the x-axis, that change in momentum?
Wouldn't it be across the y-axis or along it? I mean,
Yep, it's along the y-axis. That's the only dimension here where we see any change in momentum. Okay. Conservation of linear momentum. So for an impulse of 0, in other words, there's no change in momentum, we're going to find that the momentum remains constant. Closed, isolated system, not interacting with anything else. What that means is that if there is no net external force acting on a system of particles, then the total linear momentum of that system cannot change. It's going to remain the same. That is another way of saying conservation. Momentum is conserved. It's not lost. So if the component of the net external force on a closed system is 0 along the axis, then the component of the linear momentum along that axis cannot change. In other words, unless you've got a force acting along a particular axis that's going to change momentum in that direction, then it just won't change. Internal forces can change momenta of parts of the system, but it doesn't change the linear momentum of the entire system. Obviously, it doesn't want you to confuse momentum and energy. Energy is going to be something a little bit different. So, an initially stationary device lying along a frictionless floor explodes into two pieces. So let's say for whatever reason you've got a hockey puck and somebody decides, hey, I think it'd be a good idea to put some C4 in there, and then it detonates and it breaks apart into two pieces, which starts sliding across the floor. One of them, you know, goes in the positive X direction. What is the sum of the momenta of the two pieces after the explosion? Now, I will give you a hint here. The momentum that you saw before the explosion has to be the same as the momentum you saw after the explosion. Was the object moving before the explosion?
No, so the sum would be 0.
That's right. So now that one of those pieces is in motion in a particular direction, the other piece has to be in motion. And how is it in motion? It's in motion enough to cancel out the momentum of the first piece. Now, part B, can the second piece move at an angle to the x-axis? If we've got one piece or fragment that's moving along the positive x-axis, can the other piece be moving at an angle to that x-axis?
No, right?
That's right, no. It has to be moving along that x-axis. The question is, which direction is it moving?
The first one's positive, would it be in a negative X direction?
That's right. It has to move in the negative X direction, otherwise the momentum can't be conserved. So, doing good, doing good. All right, so types of collisions. So we have elastic collisions, where the total kinetic energy is unchanged. In other words, the energy is conserved, and it's considered to be a useful approximation for many situations. And in real collisions, you're always going to have some energy that's transferred. So that's just kind of a fact of life. Inelastic collisions are those collisions in which some energy is transferred. So if we want to get down to looking at completely inelastic collisions, those objects stick together, and that's where you're going to see the greatest loss of kinetic energy. So let's take a look here, and for some reason it decides to start out with inelastic collisions here for examples. I'm not quite sure why, but that's what they do. So for inelastic collisions, the product of the mass and the initial velocity of object 1 plus the product of the mass and velocity of object 2 initially is going to be equal to the mass and final velocity of object 1 plus the mass and velocity, final velocity of object 2. If you have a completely inelastic collision for a target, so what you're aiming at there, at rest, then what you're going to find is the momentum of the first object will end up being the same as the velocity of the combined wreck that is object 1 and object 2. So you've got, let's take a look at figure 9.14, the one on the left here first. Here you've got a generic setup for an inelastic collision. Again, some energy is transferred. So you've got object 1 coming in at an initial velocity, and then you've got object 2, which is going at its initial velocity. They make contact, and now each are moving at different final velocities than what they were before. That is going to be an inelastic collision. If it's completely inelastic, you're going to see what's going on here on the right. You've got a projectile, you've got a target, target's not moving, and then as M1 comes in, it merges with M2, sometimes neatly, sometimes not, and then they move off as a unit afterwards. So you've got the initial velocity of object 1, and then you've got the final velocity of the sum of the two objects. The center of mass, or the velocity of the center of mass, is going to remain unchanged. So initially, you've got the combined momentum here of M1 plus M2. That's going to be equal to the individual momentums divided by that same summary. Let me see if I can expand this up a little bit. So here's a graph, or here's a picture of what's going on when objects collide in a completely inelastic collision, and how does their center of mass change. So you've got a stationary target here, and then you've got a mass M1 that's coming in at a particular velocity. The center of mass is going to end up being in between those two. Also, the velocity of the center of mass is going to be pointing this direction. Obviously, this object isn't moving. This object is moving in this direction. Center of mass is going to be moving this way, but it's not going to be moving quite as fast as M1, and it's certainly going to be a little bit faster than M2. So the object comes in, and then as it gets closer and closer here, you notice that the velocity of the center of mass comes in, and eventually, boom, we have the collision. Now this moves off as a combined unit. And whatever this velocity is going to be the same as the velocity of the center of mass. What this is saying here is that the center of mass moves at the same velocity even after the bodies get stuck together. And I think that's kind of wild. So here we go. Bet you weren't expecting so many little pop quizzes as we were going through the lecture. So body 1 and body 2 are in a completely inelastic one-dimensional collision. What is their final momentum if their initial momenta are respectively 10 kilograms meters per second and 0? What would
If
be?
it's completely inelastic, wouldn't it be 10?
That's right. And what about if they were 10 kilogram meters per second and 4 kilogram meters per second?
14?
And then what about 10 kilogram meters per second and minus 4 kilogram meters per second?
6?
That's right. Okay. Total kinetic energy is conserved in elastic collisions. So in an elastic collision, the kinetic energy of each colliding body may change. In other words, the energy of the objects before collision may not necessarily be the same as what they are afterwards, but the total kinetic energy of the system does not change. So if you've got a stationary target, then you've got your laws of conservation. The first one is going to be linear momentum. And then the second is going to be the kinetic energy. And the reason you don't have an initial velocity for the second object is because it's not moving, at least initially. So your generic setup for an elastic collision with a stationary target. Afterwards, it ends up looking something like this, where both are in motion, but they have different velocities. So if you work the algebra out, you can see how the initial and the final velocities of object 1 relate to each other. You can also see how the initial velocity of object 1 and the final velocity of object 2 are related. The results of this, if you have equal masses, look at what happens here. The final velocity of object 1 is 0. The final velocity of object 2 is going to be the same as the initial velocity of object 1. In other words, what happens is the velocity of the object that comes in and makes contact with an equal mass object of the other, all of that velocity gets transferred into the second object. And that first object stops. You may have seen, are you a pool player?
I've played before, yeah.
Okay. That is a really good way to sort of visualize what's going on here. You've got a cue ball, which is supposed to be about as big as the others, but sometimes it seems to me it's a little bit smaller. But if they were the same, and you strike your cue stick on one ball and it goes over and hits the other in a line, it will transfer its velocity to the other. So if you have a massive target, in other words, let's say you're taking the cue ball and you're, for whatever reason, trying to strike a bowling ball, then the first object just bounces back and your speed is mostly unchanged. And that is just simply because your target is just so massive compared to what your projectile is. So what happens if you've got a projectile that is very, very massive and comes in and strikes a small target? Roughly, the velocities of initial and final for that massive projectile are going to be about the same. But the final velocity of object 2 is going to be about twice the velocity of object 1. Obviously, it's going to vary a little bit depending on exactly how massive they are. But in other words, that target is going to fly forward with about twice the speed. So now, if you want to take those equations and rearrange them for a target that is also moving, this is what you would end up with. So those you might want to log down somehow. So let's say you've got an elastic collision with moving targets. You see their initial velocities there in that picture. So let's see, it says 918 is going to be the picture here. So we're going to take this picture right here. So what is the final linear momentum of the target in figure 918 if the initial linear momentum of the projectile is 6 kilograms times meters per second, and the final linear momentum of the projectile is 2 kilogram meters per second. So you've got a projectile which comes in with a linear momentum of 6, and then after it makes the collision, then the final is going to be 2 kilogram meters per second squared. So what is going to be the final linear momentum of the target? So you've got the object coming in, strikes here, and it goes from 6 down to 2. What's going to happen? What's this object's linear momentum going to be?
4?
Right. What if the what if the final linear momentum of the projectile happens to be minus 2 kilogram meters per second squared? What would be the final linear momentum of that object, of that projectile? So you've got this object coming in, it's coming in at 6 kilogram meters per second squared. And then after it strikes the target, it's moving back this direction at minus 2. So it's gone from 6 to minus 2. What's going to be the linear momentum of this one?
8?
That's right. It's going to be 8. What's going to be the final kinetic energy of the target if the initial and final kinetic energies of the projectile is going to be 5 joules and then gets reduced down to 2 joules? So again, the object comes in, it's got 5 joules of energy, strikes this, which didn't have any energy to begin with, and now this is sitting at 2 joules. What's going to be the kinetic energy here?
3 joules?
That's right. Now, to make things even more complicated, we're going to apply the conservation of momentum along each axis. So we're going to apply it for energy for elastic collisions. So we've got something that comes in this direction, but doesn't quite come in solidly enough to contact this to have it spin out this way. In this particular case, object 2 spins up this way because this came in at an angle. And when it comes in at an angle, the projectile goes off this way, the target ends up going this way. In this particular type of situation, in this collision, both momentum and kinetic energy are going to be conserved. You're going to start seeing some dependencies on these two angles as far as to which path they're taking. So if you go through and you work through the math, obviously the second object was not in motion at the beginning, but the first object was. And then if you want to get an idea as to what the momentum was in the x direction, instead of just having m1 v1 plus m2 v2, you're now taking the cosine of this particular angle into consideration. You're taking the cosine of this angle. The cosine of that angle is basically going to be the x component of that vector. And then if you take the cosine of theta 2, it's going to be that component lying along this line. In the y direction, neither object were moving initially. That's why the momentum here is considered to be 0. However, once the objects are in motion, you've got this object which is moving in the negative y direction, and that would be considered its momentum, because if you look at the sine of this particular angle, it's going to be the opposite, this leg right over here. And this answer, or this term, is going to be negative. Over here, this is going to be positive, as it reflects this object moving in this direction, which is going to be positive in the y direction. The energy in this particular case, the energy is the energy. It's not really a vector component as we see it. Since the second object was not moving, all we started out with here was the first object's kinetic energy. Since it's conserved, this is going to be equal to the sum of the kinetic energy of the objects after they've been hit. Those are a lot of equations, and those 3 equations for the stationary target have 7 unknowns. So if you go through here, you've got the initial and the final velocity of 1, you've got the initial and final velocity of 2, you've got angle 1, you've got angle 2, you've got M1 and M2, and I'm trying to find the 7th variable here. It's not jumping out at me immediately. I know those 2 angles. Maybe it's just the velocity final, velocity initial. That would be 4, 5, 6. And I'm struggling to figure out what the 7th one is. I should see it, but I don't. Oh, wait. The final velocity here. No, the initial velocity of that one is missing. That's the key thing right there. So it would be this, this, and that. Okay. All right. So that's the 7 variables we're talking about. As long as you know 4 of them, you can solve for the remaining ones. So in figure 9.21, suppose that a projectile has an initial momentum of this, has a final x component of momentum of 4, and a final y component momentum of 3. So for the target, what's the final x component of the momentum and then the final y component? Well, if we look at this again, was this object moving in the y direction when it was coming in?
It wasn't.
It wasn't. So if it's not moving in the y direction, that means all of its initial momentum is coming in the x direction. So if it's coming in the x direction at 6, and it ends up having a final momentum of 4, what's the change in the momentum for the target in the x direction?
2?
That's right. It'll be 2 because it's the difference between those 2. Now, let's look at the y direction. If the final y component of the projectile has a -3 kg/m per second, what's the final y component for the target? Since this object wasn't moving in the y direction, it gave a change in momentum to this object of being -3 in this direction. since there was no change in momentum initially, but now there's -3 going in this direction, what must be happening here?
So it'd be 3, right?
Right, it'd be 3, a +3, to counterbalance the negative here. All right. So for the final section here, we've got systems with varying mass, and a rocket is a pretty good example. So a rocket and exhaust products form an isolated system. They do conserve momentum, and if you rewrite this, the mass of everything times the velocity, basically everything riding in the rocket, is going to end up being the same as the change in the mass times u, which is going to be a relative speed, plus the change of the mass plus the change in the mass times the velocity plus the change in velocity. That u is going to be defined as the velocity plus its change minus any sort of relative velocity, since you're looking at a reference frame that's moving. So here's a picture of what's going on. The ejection of mass from the rocket increases the rocket speed. So you've got mass that's being thrown out this way. The way it's shown here is that you've got mass plus whatever the change is, and then you've got the velocity plus whatever the change in velocity is as it moves in this direction. So the first rocket equation, where R is going to be the mass rate of fuel consumption, is going to be R times the velocity, the relative velocity is going to be equal to mass times the acceleration. This is going to be considered thrust. And then if you were to go through and derive the velocity change for a given consumption of fuel as the second rocket equation, this is what you will come up with. Here at the end, we have a summary, and I will go ahead and post all of the notes on this so that you can have it as a handy guide. You got any questions?
Not really. It's just going to take some practice to get to fully understand these questions.
It will. It will. I think going over a lot of the examples that the book has is probably going to be your best bet, because that will focus your attention in, so you can kind of see the concepts. But from the feedback that I've seen from you, I think you kind of get the simple problems that are put forward here, which is a good thing. So if you do have any questions going forward, there's the muddiest point where you can post them out there, and we can kind of work through those. That's all I was going to go through tonight. Do you have anything else you want to bring up?
Not really.
Okay. All right. Well, I'm going to go ahead and let you go. If you do think of anything else or have anything else, don't hesitate to contact me.
Of course, yeah.
All right. Have a good one, and I hope quarantine doesn't get too boring for you.
Yeah, I got some fun roommates I can deal with.
Well, there you go.
Yeah, so it's not completely boring.
Okay.
Yeah, you have a good one.
All right, you too.